We think we understand Earth's story. A planet born from cosmic dust, slowly cooling, then spawning the first simple life forms that eventually evolved into the dinosaurs we know so well. Then came mammals, and finally us. It's a neat timeline that stretches back hundreds of millions of years, each chapter building logically on the last. But what if that story is incomplete? What if long before the first dinosaur drew breath, long before we think complex life was even possible, Earth had already hosted something extraordinary? A civilization that rose, flourished, and then vanished so completely that we've never even thought to look for it. If that were true, how would we know? And more importantly, what would it mean for everything we believe about life, intelligence, and our place in the universe? We live in a world where Earth's history feels like a well-understood book. Open any geology textbook and the story unfolds in orderly chapters. The formation of the planet 4.5 billion years ago, the emergence of simple bacteria, the rise of complex cells, then plants, then animals, and finally the age of dinosaurs, beginning around 230 million years ago. It all makes sense on paper. A logical progression that suggests intelligence is a recent innovation, something that appeared only in the last few million years with early humans. But sometimes the most logical stories are built on incomplete information, because our understanding of Earth's deep past isn't based on knowing everything that ever happened. It's based on what little evidence has survived the relentless march of geological time, and what we've been lucky enough to find. Here's the question most people never think to ask. What if our timeline is missing something profound? Not just a forgotten species or an unusual ecosystem, but an entire chapter of Earth's history. A chapter so ancient, so thoroughly erased by time, that it predates the dinosaurs by hundreds of millions of years. Could Earth have once hosted an intelligent civilization 500 million years ago? The idea sounds impossible at first. We imagine that time as dominated by simple sea creatures, primitive organisms that had barely crawled onto land. But that image is built entirely on what the fossil record has preserved. And the fossil record, as we'll discover, is far more incomplete than most people realize. The problem is fundamental. The deeper into Earth's past we go, the less there is to find. Over hundreds of millions of years, the planet's surface has been recycled dozens of times through plate tectonics. Continents have moved, oceans have opened and closed, and mountain ranges have been ground to dust and rebuilt elsewhere. Even the rocks themselves get recycled, melted down in the Earth's mantle, and reformed into something entirely new. Think about our own civilization. If humanity vanished tomorrow, and 500 million years passed, what would remain? Our cities would crumble, our metals would rust away, and our plastics would break down. Forests would grow over our ruins, ice ages would come and go, and the very continents would drift to new positions. In that vast stretch of time, even our bones would likely dissolve, leaving behind nothing but the faintest chemical signatures buried in rock layers that future archaeologists might never think to examine. So when paleontologists say there's no evidence for an advanced civilization before the dinosaurs, that doesn't necessarily mean it never existed. It might mean the evidence was erased by the most thorough destroyer of all, deep time itself. This question matters because it challenges everything we assume about the rarity and fragility of intelligence. We tend to see consciousness as the universe's greatest achievement, something so unlikely that it took billions of years to develop just once on our planet. But if we're wrong, if intelligence has emerged multiple times in Earth's history, then we might not be as unique as we believe. We might not even be the first to wonder about our place in the cosmos. And if there was a civilization before the dinosaurs, we have to ask harder questions. What were they like? How did they live? What did they achieve? And most unnervingly of all, what happened to them? The question no one thinks to ask isn't just about the distant past. It's about the nature of intelligence itself. and whether consciousness might be far more common in the universe than we dare to imagine. When we talk about the time before dinosaurs, we're discussing a span so vast that it challenges human comprehension. The first dinosaurs appeared around 230 million years ago. Before that lies the Permian period, then the Carboniferous, the Devonian, and stretching back even further, the Cambrian explosion 540 million years ago, when complex life first appeared in abundance. But even the Cambrian explosion, that moment when Earth's oceans suddenly filled with diverse creatures, represents only the most recent eighth of our planet's existence. For the first 4 billion years of Earth's history, life was primarily microscopic, or at least that's what we assume based on what we've found. The challenge of studying such deep time isn't just academic, it's a fundamental problem of evidence preservation. Earth is not a museum where artifacts sit unchanged for millions of years. It's a dynamic system that constantly destroys and rebuilds its own surface. The oldest rocks on our planet date back only 4 billion years, and they're extremely rare. Most of the rock record from Earth's early history has been recycled through subduction zones, where oceanic crust plunges back into the mantle and melts. What this means is staggering. Entire continents from Earth's deep past have been completely destroyed. Mountain ranges that may have rivaled the Himalayas have been ground to nothing. Oceans that once separated supercontinents have closed up and disappeared entirely, taking with them any evidence of what might have lived along their shores. Plate tectonics operates on a scale that makes human history invisible. The Atlantic Ocean, for instance, is still growing wider at about the same rate your fingernails grow. That seems impossibly slow until you multiply it by hundreds of millions of years. In that time, continents have moved thousands of miles, collided to form supercontinents, then broken apart and scattered across the globe again. This continental drift means that any civilization existing before the dinosaurs would have lived on a planet with a completely different geography. The supercontinent Pangaea, which formed around 300 million years ago, was just the most recent in a series of supercontinents that formed and broke apart throughout Earth's history. Before Pangaea came Rodinia around 900 million years ago. Before that, Columbia around 1.8 billion years ago. Each time these massive landmasses assembled and dispersed, they carried with them any traces of whatever might have existed on their surfaces. Erosion works hand in hand with tectonics to erase the past. Wind and water are surprisingly powerful forces when given enough time. The Appalachian Mountains, once as tall as the Himalayas, have been worn down to gentle hills. The Canadian Shield, one of Earth's oldest stable regions, has been scraped nearly flat by billions of years of weathering. Even the hardest granite, given enough time, crumbles to sand. But perhaps the most thorough destroyer is metamorphism, the process by which existing rocks are transformed by heat and pressure. When rocks are buried deep enough or subjected to intense temperatures, their original structure is completely altered. Sedimentary layers that might have contained fossils are recrystallized into metamorphic rocks, where no trace of their original contents remains. The result is that Earth's deep past is like a book where most of the pages have been torn out, and many of the remaining pages have been so damaged that they're impossible to read. We're left with fragments, scattered pieces that give us glimpses of what ancient Earth was like, but never the complete picture. This is why the absence of evidence from hundreds of millions of years ago tells us very little about what actually happened. The planet itself has been too efficient at erasing its own history. If we could step into a time machine and visit Earth 500 million years ago, we would find ourselves on an alien world. This was the early Cambrian period, a time when our planet's geography, climate, and life forms bore little resemblance to anything we know today. The continents themselves were unrecognizable. Most of Earth's land masses were clustered in the southern hemisphere, with vast stretches of ocean covering much of what would become the northern continents. There were no ice caps at the poles. Instead, Earth enjoyed a greenhouse climate with temperatures significantly warmer than today. Sea levels were much higher, flooding low-lying areas and creating shallow, warm seas that covered much of the continental shelves. The atmosphere was different too. Oxygen levels were lower than today, perhaps only half of what we're used to. This might seem like a barrier to complex life, but many organisms have adapted to low oxygen environments throughout Earth's history. Carbon dioxide levels were much higher, contributing to the greenhouse effect that kept the planet warm even at high latitudes. But the most striking difference would be the landscape itself. There were no forests, no grasslands, no flowers or trees. The land was largely barren, a rocky wasteland broken only by rivers, lakes, and the occasional patch of primitive moss or lichen. Most complex life was confined to the oceans, where the Cambrian explosion was just beginning to populate the seas with strange new creatures. In the water, however, life was already remarkably diverse and sophisticated. Trilobites scuttled across the seafloor with complex compound eyes that could detect polarized light. Anomalocaris, a predator up to 6 feet long, hunted with grasping arms and sophisticated sensory organs. Early vertebrates like Hycuichses had already developed primitive nervous systems and the beginnings of a backbone. What's crucial to understand is that these creatures weren't simple by any measure we would recognize today. Trilobites had some of the most advanced eyes ever evolved, with calcite lenses that could focus light more effectively than many modern optical instruments. Some species had behavioral patterns that suggested social cooperation and even primitive forms of communication. The ocean ecosystems of 500 million years ago were complex webs of predation, competition, and cooperation. There were filter feeders, active hunters, scavengers, and burrowing specialists. Some creatures built reefs, others created elaborate burrow systems, and many displayed sophisticated defensive strategies. Yet for all this complexity, there's something missing from our picture of Cambrian Earth. The fossil record from this time, while rich compared to earlier periods, still represents only a tiny fraction of the life that must have existed. Soft-bodied organisms rarely fossilize, and the vast majority of ancient environments are simply not preserved in rock formations we can access today. This creates an enormous gap in our knowledge. We know that life 500 million years ago was already capable of remarkable achievements, sophisticated sensory systems, complex behaviors, and intricate ecological relationships. But we have almost no information about what might have existed in environments that weren't conducive to fossil formation. Could there have been something more? Some form of life that developed along paths we've never imagined? The Cambrian period shows us that evolution was already capable of extraordinary innovation 500 million years ago. The question is whether that innovation might have produced something we would recognize as intelligence, in environments where no trace of it could survive to the present day. When most people think about ancient life, they picture museum displays filled with dinosaur skeletons, perfectly preserved specimens that give us detailed windows into the past. But these impressive fossils create a misleading impression about how complete our knowledge of Earth's history really is. The truth is that fossilization is an extraordinarily rare event, and the deeper into the past we look, the more incomplete the record becomes. For an organism to become a fossil, a very specific set of conditions must be met. The creature must die in an environment where it can be quickly buried by sediment, protecting it from scavengers and decay. The sediment must be fine enough to preserve details, but not so acidic that it dissolves bones or shells. The area must then remain geologically stable for millions of years, avoiding the heat and pressure that would destroy the fossil. Finally, the fossil must be exposed by erosion or excavation in a place where humans happen to be looking for it. Given these requirements, it's estimated that less than 0.1% of all species that ever lived have left any fossil traces at all. And that percentage drops dramatically as we go further back in time. The fossil record from 500 million years ago represents an almost infinitesimally small sample of the life that actually existed. The bias towards certain types of preservation is also severe. Hard parts like bones, shells, and teeth are far more likely to fossilize than soft tissues. This means our picture of ancient life is heavily skewed toward organisms with durable skeletons. Soft-bodied creatures, no matter how complex or numerous they might have been, are rarely preserved. When they are, it's considered an exceptional discovery worthy of scientific papers and museum exhibitions. Think about what this means for our understanding of intelligence in the deep past. The most intelligent creatures alive today, octopuses, dolphins, and great apes, have either no hard parts or skeletal structures that preserve poorly. An octopus has no bones, no shell, no teeth. If octopuses went extinct today, future paleontologists might never know they existed, despite their remarkable problem-solving abilities, use of tools, and complex behaviors. This preservation bias becomes even more pronounced when we consider the environments where intelligent life might be most likely to develop. Coastal areas, river deltas, and lake shores provide rich resources and diverse ecological niches that could support complex organisms. But these are also environments where fossilization is less likely to occur. The constant movement of water tends to scatter remains before they can be buried and preserved. There's also a geographic bias in the fossil record. Most paleontological work has focused on areas that are easily accessible and known to contain fossils. Vast regions of the world, particularly in the deep ocean basins, and areas covered by thick vegetation or ice, remain largely unexplored. The ocean floors where much of ancient life existed are constantly being recycled through plate tectonics, destroying any evidence they might have contained. Time compounds all these problems. The further back we go, the more likely it is that any evidence has been destroyed by metamorphism, erosion, or tectonic activity. Rock formations from 500 million years ago are rare, and those that do exist often show signs of having been altered by heat, pressure, or chemical processes that would obliterate any trace of complex organic structures. Perhaps most importantly, the fossil record is biased toward what we expect to find. Paleontologists look for certain types of sites and certain types of remains based on existing theories about how evolution proceeded. If intelligence had evolved along completely different lines, producing organisms unlike anything in our current understanding of biology, we might not recognize the evidence even if we found it. The limitations of the fossil record don't prove that intelligence existed before the dinosaurs, but they do demonstrate that its absence from our current understanding proves nothing. We're looking at Earth's ancient history through a keyhole, seeing only the tiniest fraction of what actually existed. In that vast darkness beyond our vision, anything might have been possible. If we're looking for a moment in Earth's history when evidence of an ancient civilization might have been completely erased, we need look no further than the event that ended the Permian period 252 million years ago. Known as the Great Dying, this was the most severe mass extinction in Earth's history, eliminating up to 96% of all marine species and 70% of terrestrial vertebrates. It was so catastrophic that it nearly ended complex life on our planet entirely. But the Permian extinction wasn't just a biological catastrophe, it was also a geological one that fundamentally transformed Earth's surface and atmosphere. If any trace of pre-dinosaur intelligence had survived the previous 250 million years of erosion and plate tectonics, this event would have been the final destroyer, erasing evidence so thoroughly that we might never suspect it had existed. The extinction was triggered by the massive volcanic eruptions in what is now Siberia. The Siberian traps, as they're known today, were not ordinary volcanic activity. They represented one of the largest volcanic events in Earth's history, spewing out over 4 million cubic kilometers of lava and covering an area roughly the size of Europe. The eruptions continued for nearly 1 million years, fundamentally altering the planet's climate and chemistry. The immediate effects were devastating. Volcanic ash and sulfur dioxide blocked sunlight, causing global cooling and acid rain that poisoned both land and sea. But the long-term effects were even worse. The eruptions released enormous quantities of carbon dioxide and methane, creating a runaway greenhouse effect that raised global temperatures by 8 to 10 degrees Celsius. Ocean pH dropped dramatically, making the seas acidic enough to dissolve the shells of marine organisms. Perhaps most crucially for our question, the eruptions also released massive amounts of toxic gases, including hydrogen sulfide, mercury, and other heavy metals. These chemicals would have contaminated soil and water across vast areas, making much of the planet uninhabitable for complex life. Any civilization existing at the time would have faced environmental destruction on a scale that dwarfs even our worst climate change scenarios. The Permian extinction also triggered massive changes in sea level and ocean circulation. The formation of the supercontinent Pangaea had already begun to disrupt ocean currents, but the extinction event accelerated these changes. Shallow seas that had supported diverse ecosystems drained away, while new ocean basins opened in other areas. Entire continental shelves were exposed and then flooded again as ice caps melted and reformed. But beyond the immediate destruction, the Permian extinction set in motion geological processes that would have systematically erased evidence of whatever came before. The massive volcanic activity created new rock layers that buried older formations under kilometers of basalt and ash. The climate changes accelerated erosion and weathering, breaking down existing rock formations and redistributing their components across the planet. The extinction also marked a fundamental shift in the types of organisms that dominated Earth's ecosystems. The complex communities of the late Permian, with their diverse predators, herbivores, and decomposers, were replaced by much simpler assemblages dominated by just a few species. This ecological simplification lasted for millions of years and may have eliminated not just species, but entire ways of life that we can no longer imagine. Recovery from the Great Dying was slow and incomplete. It took nearly 10 million years for biodiversity to begin returning to pre-extinction levels, and many evolutionary lineages that had existed for hundreds of millions of years were gone forever. The survivors that eventually gave rise to dinosaurs and mammals were fundamentally different from what had come before. If an intelligent civilization had existed before the Permian extinction, this event would have been their apocalypse. Not just a collapse of their society, but a transformation of the planet so complete that even their fossilized remains might have been destroyed. The Great Dying represents a geological reset button, a moment when Earth's surface was so thoroughly altered that almost no trace of the previous 250 million years survived in recognizable form. This doesn't prove that such a civilization existed, but it does provide a plausible explanation for why we might never find evidence of it. The same processes that nearly ended all life on Earth would have been more than capable of erasing any trace of intelligence that had evolved in the hundreds of millions of years before dinosaurs first appeared. When we imagine ancient intelligence, we inevitably picture something familiar. Bipedal creatures using tools, building structures, perhaps even developing language and culture. But this anthropocentric view might be blinding us to possibilities that are far stranger and more wonderful than anything in our experience. Evolution is not a ladder with humans at the top, but a vast tree with countless branches, most of which lead to ways of life we can barely comprehend. If intelligence had evolved 500 million years ago, it almost certainly would have taken forms unlike anything that exists today. The environmental pressures, available materials, and evolutionary starting points were completely different from those that shaped human consciousness. Consider the ocean-dominated world of the Cambrian period. In this environment, intelligence might have developed along entirely aquatic lines. We already know that some marine animals today display remarkable cognitive abilities. Octopuses can solve complex puzzles, use tools, and even appear to plan for future events. Dolphins have sophisticated social structures and communication systems, but these creatures evolved from ancestors that lived on land before returning to the sea. An intelligence that evolved directly in the ocean, without ever experiencing terrestrial life, might be almost unrecognizable to us. They might have developed distributed nervous systems spread throughout their bodies, rather than centralized brains. Their communication could be based on chemical signals, bioluminescence, or pressure waves rather than sound or vision. Their technology might be entirely biological, using living organisms as tools rather than manufactured devices. Such creatures might never have developed the concept of permanent structures. Instead, they could have created temporary arrangements of living organisms that dissolved and reformed as needed. Their achievements might be measured not in monuments or artifacts, but in the complexity of the ecological systems they orchestrated. They could have practiced a form of agriculture based on managing entire ocean ecosystems, directing the evolution of other species to serve their purposes. Another possibility is that ancient intelligence developed among creatures we would consider impossibly alien. The trilobites, for instance, had existed for over 250 million years before going extinct, longer than any other complex animal group in Earth's history. Some species had incredibly sophisticated sensory systems and showed evidence of complex behaviors. What if their long evolutionary history had eventually produced forms of consciousness we couldn't recognize? Trilobite intelligence might have been based on entirely different principles from vertebrate intelligence. Their compound eyes could detect polarized light and see ultraviolet wavelengths invisible to us. They might have developed forms of navigation and communication based on electromagnetic fields or quantum effects. Their social structures could have been based on chemical signaling so subtle that we would interpret it as purely instinctual behavior. There's also the possibility that ancient intelligence was collective, rather than individual. Many modern organisms, from ant colonies to forest ecosystems, display emergent behaviors that seem almost intelligent when viewed as a whole. What if evolution had produced truly conscious collective organisms hundreds of millions of years ago? These might have been composed of millions of individual creatures that functioned as neurons in a planet-spanning brain. Such a collective intelligence would leave no fossils in any recognizable sense. There would be no individual bodies to preserve, no tools in any form we would understand. Their achievements might be visible only as subtle patterns in the distribution of other species, or as geological formations that we would interpret as purely natural. They might have been capable of incredible feats of environmental engineering, while leaving behind no trace that we could recognize as artificial. The crucial point is that intelligence is not a human invention. It's a natural phenomenon that emerges from the complex organization of information processing systems. Given enough time and the right environmental pressures, it could evolve in ways we haven't even imagined. The vast majority of evolutionary possibilities remain unexplored, and consciousness might be far more common and diverse than we assume. If we limit our search for ancient intelligence to human-like creatures using human-like technologies, we might miss evidence that is hiding in plain sight, waiting for us to develop the conceptual frameworks necessary to recognize it for what it truly is. Our search for evidence of ancient intelligence is handicapped by our assumptions about what technology should look like. We imagine metal tools, stone monuments, and manufactured objects, because those are the technologies our species has developed. But intelligence could have emerged along completely different technological paths, creating achievements that would be invisible to archaeologists looking for familiar artifacts. Biology offers examples of technologies that far exceed human engineering in many ways. Spider silk is stronger than steel cable by weight. The compound eyes of trilobites focus light more effectively than most modern optical instruments. Some bacteria can perform quantum computations to navigate using magnetic fields. If ancient intelligence had mastered biotechnology instead of metallurgy, their greatest achievements might have been indistinguishable from natural evolution. Consider what a biotechnological civilization might accomplish. Instead of mining metals from the ground, they could have bred specialized organisms that concentrated useful materials from seawater or soil. Rather than building with stone or concrete, they might have grown living structures that were self-repairing and adaptive. Their transportation systems could have been based on domesticated creatures, or even modified versions of themselves, optimized for different environments. Such a civilization would leave almost no archaeological trace. Their buildings would have decayed like any other organic matter. Their tools would have been alive and would have died with their creators. Even their most impressive achievements might appear to be natural phenomena to future observers who didn't understand the principles behind them. Information storage and processing might have taken entirely different forms as well. Instead of writing on stone or paper, they could have encoded knowledge in the genetic sequences of specially designed organisms. Libraries might have been ecosystems, where different species carried different types of information, creating living databases that could evolve and update themselves over time. Their computing systems might have been based on the neural networks of colonial organisms or the chemical processing capabilities of specialized biological structures. These organic computers could potentially have been far more powerful than anything we've developed, capable of processing information in ways we're only beginning to understand through our study of biological neural networks. Energy production in such a civilization might have relied entirely on biological processes. They could have developed organisms capable of highly efficient photosynthesis, or creatures that generated energy from chemical reactions, heat differentials, or even radioactive decay. Their power grid might have been a network of living organisms distributing energy through biological channels rather than metal wires. Even their manufacturing capabilities might have been completely organic. Instead of factories, they could have used specially evolved organisms that grew products to precise specifications. Their material science might have been based on understanding and directing the natural processes that create everything from pearls to bone to the incredibly strong adhesives produced by marine organisms. The transportation technology of such a civilization could have been equally foreign to our experience. Rather than building vehicles, they might have domesticated or created organisms capable of carrying them across land, sea, or even air. These biological vehicles could have been far more efficient and environmentally sustainable than anything in our mechanical transportation systems. Perhaps most importantly, their communication technologies might have been based on principles we're only beginning to discover. Recent research has shown that many organisms can communicate through quantum entanglement, electromagnetic fields, and chemical signals that travel vast distances. An ancient biotechnological civilization might have developed these natural communication methods into sophisticated networks that spanned continents or even the entire planet. The traces of such technologies would be almost impossible to detect after hundreds of millions of years. Unlike metal tools or stone buildings, biological technologies would have completely decomposed, leaving behind at most some subtle chemical signatures in ancient rock formations. Their greatest engineering projects might be indistinguishable from natural geological formations, and their most sophisticated tools might appear to be the products of normal evolution. This doesn't mean such a civilization definitely existed, but it illustrates how our search for ancient intelligence might be fundamentally limited by our assumptions about what intelligence creates. If we're looking for hammers and wheels and writing systems, we might miss evidence of achievements that dwarf our own technological capabilities, while leaving no trace we could recognize. If evidence of pre-dinosaur intelligence exists anywhere on Earth, the most likely place to find it would be the deep ocean floor. This is the planet's largest and least explored environment, covering more than 60% of Earth's surface, yet remaining almost entirely unmapped and unstudied. What makes the ocean floor particularly intriguing for our question is that it preserves conditions and materials from Earth's distant past better than any terrestrial environment. The deep ocean is a world of eternal darkness and crushing pressure, but it's also a world of remarkable stability. Temperatures vary by only a few degrees across vast areas. Ocean currents flow in predictable patterns that have remained largely unchanged for millions of years. Most importantly, the deep sea floor is protected from the erosion, weathering, and biological activity that destroy evidence on land. Sediments accumulate on the ocean floor at incredibly slow rates, sometimes only a few centimeters every 1,000 years. This means that layers representing millions of years of Earth's history are preserved in relatively undisturbed sequences. In the deepest parts of the ocean, sediment cores can contain material dating back hundreds of millions of years, creating archives of ancient conditions that exist nowhere else on the planet. But here's what makes the ocean floor truly mysterious. We've explored less than 5% of it in any detail. Our maps of the seafloor are less detailed than our maps of Mars. Vast areas of the deep ocean have never been visited by humans or even by robotic probes. We literally know more about the surface of the moon than we do about the bottom of our own oceans. This ignorance isn't just a matter of scientific curiosity. The ocean floor contains geological formations, chemical deposits, and biological communities that could revolutionize our understanding of Earth's history. Deep-sea trenches preserve rocks that are among the oldest on the planet. Hydrothermal vents create unique chemical environments that might preserve evidence of ancient life forms. Abyssal plains contain sediment sequences that record the planet's environmental changes over hundreds of millions of years. Recent discoveries have shown just how much we're missing. In 2020, scientists discovered the longest mountain range on Earth, stretching 65,000 kilometers along the ocean floor. In 2019, they found evidence of plate tectonic activity from over 3 billion years ago preserved in seafloor rocks. Every deep-sea expedition reveals new species, new geological formations, and new insights into how our planet works. The technology needed to explore the deep ocean is extraordinarily complex and expensive. The pressure at the bottom of the deepest trenches is more than 1,000 times greater than at sea level, enough to crush any normal submarine instantly. The darkness is complete, requiring artificial lighting for any observation. The distances involved are vast, and communication with the surface is limited to slow, low-bandwidth acoustic signals. These challenges mean that deep ocean exploration proceeds at a glacial pace. Each dive by a deep-sea submersible covers only a tiny area and can examine only the surface of the sea floor. Actually excavating into the sediment layers that might contain evidence of ancient activity requires even more specialized equipment that exists in only a few research facilities worldwide. Yet the potential discoveries waiting in the deep ocean could be extraordinary. If an ancient civilization had existed, evidence of their activities might be preserved in seafloor sediments. Chemical signatures from their industrial processes could be locked in ancient rock layers. Structures they built might still exist in the stable, cold environment of the deep sea, protected from the geological processes that erase evidence on land. The ocean floor might also preserve evidence of the environmental changes that ended such a civilization. The chemical signatures of mass extinctions, climate changes, and even asteroid impacts are often better preserved in marine sediments than in terrestrial rocks. If something catastrophic ended a pre-dinosaur civilization, the evidence might be waiting in the deep-sea sediment cores we've never thought to examine with this possibility in mind. Most intriguingly, the deep ocean might contain evidence of life forms we've never imagined. The recent discovery of complex ecosystems around hydrothermal vents, thriving in conditions that were thought to be impossible for life, suggests that our understanding of biology is still very incomplete. If intelligence had evolved in the ancient oceans, traces of it might still exist in forms we wouldn't recognize as artificial. The ocean floor represents the planet's greatest frontier, a world as alien and unexplored as any distant planet. Until we develop the technology and commitment to truly map and explore these vast underwater landscapes, we'll never know what evidence of Earth's deep history might be waiting in the darkness below. Throughout Earth's geological record, there are discoveries that seem to challenge our understanding of when complex life developed. These anomalies aren't necessarily evidence of ancient intelligence, but they remind us that the history of life on our planet may be far stranger and more complex than our textbooks suggest. One of the most puzzling discoveries involves structures called stromatolites, layered formations created by ancient bacteria. While most stromatolites are clearly biological, some of the oldest examples, dating back over 3 billion years, show patterns of organization that seem almost too complex for simple microorganisms. The structures display geometric precision and organizational principles that suggest a level of coordination that challenges our understanding of what bacteria can achieve. Even more mysterious are certain mineral formations that appear in rocks from the Precambrian era, hundreds of millions of years before complex life was supposed to exist. These include perfectly spherical structures, complex crystalline formations, and mineral deposits that seem to require very specific chemical conditions to form. While most geologists assume these are natural phenomena, some display organizational patterns that are difficult to explain through purely inorganic processes. The Ediacaran biota, dating to around 570 million years ago, presents another puzzle. These were some of the first complex multicellular organisms, and they included forms unlike anything alive today. Some appear to have been enormous, reaching several meters in length, with strange fractal body plans that don't fit into any modern biological categories. They seem to represent an entirely different approach to multicellular life, one that was completely replaced by the more familiar forms that appeared during the Cambrian explosion. What makes the Ediacaran creatures particularly intriguing is that they show evidence of behaviors that seem surprisingly sophisticated for such ancient organisms. Some appear to have moved in coordinated ways across the seafloor, leaving behind trace fossils that suggest complex behavioral patterns. Others seem to have constructed elaborate burrow systems or created structures that modified their local environment in ways that benefited their survival. There are also geological anomalies that are harder to explain. Certain rock formations from the deep past show signs of having been altered in ways that seem almost engineered. Underground chambers and tunnel systems that appear too regular to be natural cave formations, mineral deposits that seem to have been concentrated or processed in ways that pure geology can't easily account for. Some of the most intriguing mysteries involve isotopic signatures in ancient rocks. Isotopes are variants of chemical elements, and their ratios in rock formations can reveal information about the conditions under which those rocks formed. Occasional scientists find isotopic signatures in ancient rocks that don't match what we would expect from purely natural processes. These could indicate unusual biological activity, extreme environmental conditions, or processes we don't yet understand. Recent discoveries in molecular paleontology have also revealed surprises. Scientists can now extract and analyze organic compounds from rocks that are hundreds of millions of years old. Some of these compounds appear to be more complex than we would expect from the simple life forms that supposedly dominated Earth at the time. There are molecular signatures that seem to indicate sophisticated biochemical processes occurring much earlier in Earth's history than our evolutionary timeline suggests. Perhaps most puzzling are certain trace fossils, evidence of ancient organism behavior rather than the organisms themselves. These include burrow systems, feeding tracks, and movement patterns preserved in ancient seafloor sediments. Some of these traces seem to indicate problem-solving behavior, environmental manipulation, and even what might be interpreted as tool use among creatures that lived hundreds of millions of years ago. None of these discoveries definitively proves the existence of ancient intelligence. Each can potentially be explained by natural processes we don't fully understand, or by the activities of complex organisms that were still far from intelligent in any sense we would recognize. But taken together, they suggest that life in the deep past may have been more sophisticated and diverse than our current theories assume. These anomalies keep alive the possibility that our understanding of Earth's ancient history is incomplete. They remind us that evolution is capable of producing surprises, and that intelligence might not be as recent or as rare as we believe. While we can't claim these mysteries as evidence of pre-dinosaur civilization, they do suggest that the deep past holds secrets we're only beginning to uncover. The Fermi paradox asks one of the most profound questions in science. If the universe is so vast and old with billions of potentially habitable planets, where is everybody? Why haven't we detected any signs of alien civilizations despite decades of searching? But there's another way to think about this puzzle, one that brings the question much closer to home. What if the universe isn't empty of intelligence at all? What if consciousness has evolved countless times throughout cosmic history, but intelligent civilizations have a natural lifespan that makes them almost impossible to detect across the vast scales of space and time? Consider the possibility that intelligence regularly emerges on planets throughout the galaxy, develops for a few million years, then vanishes due to extinction events, environmental changes, or the simple passage of deep time. If this pattern is common, then the universe could be filled with the archaeological remains of dead civilizations, most of them so ancient that even their home planets have been sterilized and reset multiple times. Earth itself might be an example of this cycle. Rather than being the first planet in our solar system to develop intelligence, we might be the latest in a series of conscious species that have inhabited our world. The deep timescales involved mean that previous civilizations could have risen and fallen millions of times over Earth's 4.5 billion year history, each one leaving behind evidence so faint that we mistake it for natural phenomena. This perspective transforms how we think about the search for extraterrestrial intelligence. Instead of looking for active civilizations broadcasting radio signals across the galaxy, we might need to search for the subtle traces left by intelligence that existed long ago, the chemical signatures of industrial activity in ancient rock layers, unusual isotopic ratios that indicate large-scale environmental manipulation, geometric patterns in geological formations that are too regular to be purely natural. The reversed Fermi paradox suggests that intelligence might be relatively common in the universe, but that it tends to be ephemeral on cosmic timescales. Civilizations rise, achieve remarkable things, then disappear, leaving behind only the faintest traces that are quickly erased by natural processes. The gap between the emergence of one intelligent species and the next might be so vast that they never overlap, never detect each other, and never realize they're part of a much larger pattern. On Earth, this cycle might have played out multiple times. An intelligent species could have evolved in the Cambrian period, thrived for millions of years, then been wiped out by the Permian extinction. Another could have emerged in the Triassic, only to be destroyed by the asteroid impact that ended the Cretaceous. Each time the planet would reset itself, evolution would begin again, and eventually new forms of consciousness would emerge with no knowledge of what came before. This doesn't just explain why we haven't found evidence of ancient Earth civilizations, it also explains why the universe seems so quiet. If intelligence typically lasts only a few million years out of billions of years of planetary history, then the chances of two civilizations existing simultaneously and being able to communicate across interstellar distances become vanishingly small. The implications are both humbling and terrifying. Humbling because it suggests that intelligence is not unique or special, but rather a natural phenomenon that emerges regularly throughout the universe. Terrifying because it implies that our own civilization is likely temporary, destined to join the countless others that have risen and fallen before us. But there's also something oddly comforting about this perspective. If we're part of a cosmic pattern of emerging consciousness, then intelligence itself might be one of the fundamental features of the universe, not a rare accident that happened only on Earth. Every planet, every star system, every galaxy might be filled with the ghosts of minds that once contemplated their place in the cosmos, just as we do now. The reversed Fermi paradox doesn't answer the question of whether a civilization existed on Earth before the dinosaurs, but it provides a framework for thinking about why such evidence would be so difficult to find. If consciousness is common but ephemeral, then the absence of obvious traces doesn't mean intelligence never existed. It might just mean we're looking at the wrong timescales and asking the wrong questions. Recent advances in geology, paleontology, and astrobiology are beginning to reveal just how much we don't know about Earth's deep history. New technologies and analytical methods are uncovering evidence of complexity in the ancient world that challenges many of our assumptions about when sophisticated processes first evolved. One of the most significant developments has been in the field of molecular paleontology, which uses advanced chemistry to analyze organic compounds preserved in ancient rocks. Scientists can now detect biological molecules in rocks that are hundreds of millions of years old, revealing information about ancient life that fossils alone could never provide. These molecular fossils, or biomarkers, are showing that complex biochemical processes existed much earlier in Earth's history than previously thought. For example, recent studies have found evidence of photosynthesis occurring nearly 3.5 billion years ago, much earlier than the traditional timeline suggested. Even more surprisingly, some researchers have detected molecular signatures that seem to indicate complex cellular structures and metabolic pathways in rocks dating back over 2 billion years. These findings suggest that life may have achieved remarkable sophistication very early in Earth's history. Advances in isotopic analysis are also revealing surprises. Scientists can now measure the ratios of different isotopes in ancient rocks with extraordinary precision, allowing them to detect subtle signatures of biological activity. Some of these isotopic patterns appear to indicate large-scale biological processes occurring in the distant past, including what might be evidence of ecosystem-level organization among ancient microorganisms. Perhaps most intriguingly, new analytical techniques are revealing patterns in ancient rock formations that seem almost too regular to be purely natural. High-resolution imaging and computer analysis can detect geometric structures, repeating patterns, and organizational principles in geological formations that were invisible to earlier generations of scientists. While most of these are likely to have natural explanations, some display characteristics that are difficult to account for through purely inorganic processes. The study of extremophile organisms, life forms that thrive in extreme environments, has also expanded our understanding of what's possible in biology. Scientists have discovered organisms living in conditions that were once thought to be completely hostile to life, in boiling water, in highly acidic solutions, under crushing pressure, and even in radioactive environments. These discoveries suggest that life might have been possible in ancient Earth environments that we previously assumed were sterile. Recent research in evolutionary biology has also revealed that complex behaviors and even apparent intelligence can evolve much more quickly than previously thought. Studies of organisms like octopuses, corvids, and even some insects have shown that sophisticated cognitive abilities can emerge in evolutionary lineages that diverge from our own hundreds of millions of years ago. This suggests that intelligence might not be the rare, difficult-to-evolve trait we once assumed it was. Advances in deep-sea exploration have been particularly revealing. New robotic submarines and deep-diving vehicles are discovering ecosystems on the ocean floor that are unlike anything previously known. These communities often display complex organizational structures and symbiotic relationships that hint at levels of biological coordination we're only beginning to understand. If such complexity exists today in environments we've barely explored, what might have existed in ancient oceans we know nothing about? Computer modeling of ancient climate and environmental conditions has also provided new insights. Scientists can now create detailed simulations of what Earth was like hundreds of millions of years ago, taking into account factors like atmospheric composition, ocean chemistry, and continental positions. These models often reveal that ancient Earth had stable, hospitable regions that could have supported complex ecosystems for millions of years. Astrobiology, the study of potential life beyond Earth, has also influenced how we think about intelligence on our own planet. The discovery of potentially habitable exoplanets has led scientists to develop new frameworks for thinking about how life and intelligence might evolve under different conditions. These frameworks often suggest that consciousness might be more common and diverse than we previously imagined. All of these advances point to the same conclusion: life on Earth has been far more complex and diverse throughout its history than we realized. The techniques we're developing to study ancient life are revealing that sophisticated biological processes, complex ecosystems, and even behaviors that approach intelligence may have existed much earlier and in much more diverse forms than our traditional understanding suggested. This doesn't prove that a technological civilization existed before the dinosaurs, but it does demonstrate that our knowledge of Earth's deep past is still evolving rapidly. Each new analytical technique, each new discovery, reveals aspects of ancient life that were previously invisible to us. In this context, the possibility that something truly extraordinary existed in the distant past becomes not just plausible, but increasingly likely as we develop better tools for looking. If a technological civilization existed hundreds of millions of years ago, the most likely evidence we might find today would not be artifacts or fossils, but chemical signatures embedded in the geological record. Unlike physical structures, which decay and crumble, certain chemical compounds and isotopic patterns can persist in rock formations for hundreds of millions of years, creating a potentially detectable fingerprint of industrial activity. Modern human civilization is leaving behind numerous chemical signatures that will be detectable long after our cities have crumbled to dust. We've introduced synthetic compounds that don't occur naturally, altered the isotopic composition of carbon in the atmosphere through fossil fuel burning, and created radioactive isotopes through nuclear technology. Some of these signatures will remain detectable in rock formations for millions of years. The question is, what chemical signatures would we expect from a non-human technological civilization, and where would we look for them? The answer depends on what kind of technology they developed, but there are some chemical fingerprints that would be difficult for any advanced civilization to avoid. Large-scale energy production, regardless of its specific mechanism, tends to create distinctive chemical signatures. If an ancient civilization burned organic matter for fuel, it would have altered the isotopic ratios of carbon and oxygen in the atmosphere, changes that would be preserved in sedimentary rocks and ice cores from that period. If they used nuclear energy, they would have created artificial isotopes that would still be detectable today, even after hundreds of millions of years. Industrial processes also leave characteristic chemical traces. Metal smelting produces distinctive combinations of elements and isotopes that don't occur naturally. The production of ceramics, glass, or other manufactured materials creates unique chemical signatures. Even biological technologies would likely involve the large-scale processing of organic compounds in ways that would alter the normal chemical cycles of carbon, nitrogen, and other elements. Perhaps most tellingly, any civilization that achieved significant size would have had to extract and concentrate resources from the environment. This process inevitably leaves behind distinctive patterns in the distribution of trace elements and minerals. Areas that were heavily mined or processed would show unusual concentrations or depletions of certain elements, patterns that could still be detectable in ancient rock formations. The challenge lies in knowing where to look and what to look for. Chemical signatures from hundreds of millions of years ago would be most likely to survive in geologically stable areas that have avoided significant metamorphism or erosion. These include certain deep ocean sediments, ancient continental cores, and formations that have been protected by being buried under thick layers of younger rock. Recent advances in analytical chemistry have made it possible to detect incredibly subtle chemical signatures in ancient rocks. Mass spectrometry can identify individual molecules in samples that are hundreds of millions of years old. Isotopic analysis can detect alterations in elemental ratios that deviate from natural patterns by tiny fractions. These techniques are sensitive enough to detect the chemical fingerprints of industrial activity even after geological processes have altered and dispersed the original signals. Some researchers have begun systematically searching for such signatures, though not specifically looking for evidence of ancient civilizations. Studies of ancient climate change, for example, often involve detailed chemical analysis of rock formations from hundreds of millions of years ago. These studies sometimes reveal unexplained chemical anomalies, unusual isotopic patterns, or concentrations of elements that don't fit standard geological models. Most of these anomalies have conventional explanations: unusual volcanic activity, rare meteorological events, or biological processes we don't fully understand. But occasionally, researchers find chemical signatures that are difficult to explain through purely natural processes. These might include sudden spikes in rare elements, isotopic patterns that suggest large-scale chemical processing, or combinations of compounds that seem to require very specific industrial-like conditions to produce. The search for chemical signatures of ancient civilization faces several challenges. First, we need to distinguish between signatures of technological activity and those produced by natural processes that we don't fully understand. Second, we need to develop techniques for detecting signatures that have been altered by hundreds of millions of years of geological processes. Third, we need to know what specific signatures to look for, which requires making assumptions about the technologies an ancient civilization might have used. Despite these challenges, chemical analysis represents our best hope for detecting evidence of pre-dinosaur intelligence. Unlike fossils or artifacts, chemical signatures can survive the most extreme geological processes. They provide a window into ancient environmental conditions that extends much further back in time than any other form of evidence. As our analytical techniques continue to improve and our understanding of ancient geochemistry deepens, we may eventually develop the ability to detect even the faintest traces of technological activity from Earth's distant past. The chemical records are there, locked in ancient rocks around the world. We just need to develop the tools and knowledge necessary to read them. The absence of evidence for pre-dinosaur civilization isn't necessarily because such evidence doesn't exist. It might be because we haven't been looking for it in the right places, in the right ways, or with the right expectations. The history of science is filled with examples of phenomena that existed long before we developed the concepts, tools, or motivation necessary to detect them. Our current scientific paradigm assumes that intelligence is a recent development in Earth's history. This assumption shapes everything from research funding priorities to the types of questions scientists think are worth asking. Paleontologists focus on understanding the evolution of known life forms rather than searching for evidence of unknown ones. Geologists study ancient rock formations to understand climate change and geological processes, not to look for signs of technological activity. This paradigm creates a self-reinforcing cycle. Because we don't expect to find evidence of ancient intelligence, we don't design our research to detect it. Because our research isn't designed to detect it, we don't find it. Because we don't find it, our assumption that it doesn't exist is reinforced, making us even less likely to look for it in the future. The institutional structure of science also works against revolutionary discoveries. Research funding is typically awarded for projects that build incrementally on existing knowledge, rather than for speculative investigations that might challenge fundamental assumptions. Scientists build careers by making discoveries within established fields, rather than by pursuing ideas that most of their colleagues consider implausible. Graduate students learn to ask questions that fit within existing theoretical frameworks, rather than questions that might require entirely new conceptual approaches. Journal editors are more likely to publish papers that confirm existing theories than those that propose radical alternatives. The peer review process, while essential for maintaining scientific standards, can also be conservative, rejecting ideas that are too far outside mainstream thinking. There are also practical barriers to searching for evidence of ancient intelligence. The kinds of investigations that might detect such evidence are often expensive, time-consuming, and technically challenging. Deep drilling projects, comprehensive chemical analysis of ancient rocks, and systematic exploration of unstudied geological formations require resources that are difficult to obtain for speculative research. The interdisciplinary nature of such a search also creates obstacles. Evidence of ancient intelligence might be found at the intersection of geology, paleontology, chemistry, archaeology, and even astrobiology. But modern science is organized into specialized fields, and few researchers have the broad knowledge necessary to recognize anomalies that might be significant across multiple disciplines. Cultural factors play a role as well. The idea of ancient advanced civilizations has been associated with pseudoscience, conspiracy theories, and fringe beliefs. This association makes mainstream scientists reluctant to pursue research that might be seen as lending credibility to unscientific ideas. The stigma attached to such topics can effectively discourage serious investigation. There's also the problem of interpretation. Even if we found chemical signatures, unusual geological formations, or other anomalies that might indicate ancient technological activity, interpreting them as evidence of intelligence would require a conceptual leap that most scientists are reluctant to make. The principle of parsimony, which favours simpler explanations over complex ones, would lead most researchers to prefer natural explanations, even for very unusual phenomena. Recent developments in several fields have begun to change this situation. The search for extraterrestrial intelligence has made it more acceptable to consider the possibility of non-human intelligence. Astrobiology has developed frameworks for thinking about how intelligence might evolve under different conditions. These developments have created intellectual space for considering the possibility that intelligence might have evolved on Earth itself, under very different conditions than those that produced human consciousness. The growing recognition that Earth's history contains many surprises has also made scientists more open to unexpected possibilities. The discovery of complex life in extreme environments, the realization that major evolutionary transitions happened more quickly than previously thought, and the recognition that the geological record is far more incomplete than once believed, have all contributed to a greater willingness to consider alternative scenarios. Perhaps most importantly, technological advances are giving us new tools for investigating Earth's deep past. Chemical analysis techniques that can detect trace compounds in rocks hundreds of millions of years old, computer models that can simulate ancient environmental conditions in unprecedented detail, deep-sea exploration technology that can access previously unreachable parts of the ocean floor. These new capabilities are creating opportunities to search for evidence that would have been undetectable just a few decades ago. As these tools become more sophisticated and more widely available, it becomes increasingly likely that someone will think to use them to search for traces of ancient intelligence. The question is not whether we're capable of finding such evidence if it exists. The question is whether we'll develop the scientific curiosity, institutional support, and conceptual frameworks necessary to make the search a serious scientific priority. When we step back from the details and look at the big picture, we can ask a more fundamental question. What are the actual odds that an intelligent civilization existed on Earth before the dinosaurs? While we can't calculate precise probabilities, we can examine the factors that would make such an occurrence more or less likely. The first factor is time. Earth has existed for 4.5 billion years, but complex multicellular life only appeared in the last 600 million years or so. If we focus on the period when complex life existed, but before dinosaurs dominated terrestrial ecosystems, we're looking at roughly 300 million years, from the late Precambrian through the Permian period. That's still an enormous span of time, equivalent to about 60 times longer than complex life has existed since the extinction of non-avian dinosaurs. In that 300 million year window, life achieved remarkable complexity. Eyes evolved multiple times, nervous systems became sophisticated enough to control complex behaviors, and some organisms developed what appear to be social structures and communication systems. The biological machinery necessary for intelligence, neurons, sensory organs, and information processing capabilities had already been invented by evolution. The question is whether any lineage had enough time and the right environmental pressures to develop true intelligence during this period. Modern humans evolved their current level of cognitive ability in roughly 2-3 million years, starting from ancestors that were already quite intelligent. If similar evolutionary pressures had existed in the ancient past, 300 million years would have provided more than enough time for intelligence to evolve many times over. Environmental factors also matter. Intelligence tends to evolve in environments that reward problem solving, social cooperation, and behavioral flexibility. The ancient Earth provided many such environments. Complex marine ecosystems with multiple trophic levels created opportunities for predator-prey arms races that drive cognitive evolution. Changing climate conditions would have rewarded organisms capable of adapting their behavior to new circumstances. The stability of ancient environments might actually have been more conducive to the evolution of intelligence than the rapidly changing conditions of more recent geological periods. Some regions of Earth remained relatively stable for tens of millions of years during the Paleozoic era, providing the kind of consistent selective pressure that could drive the evolution of increasingly sophisticated cognitive abilities. However, there are also factors that make ancient intelligence less likely. The atmospheric oxygen levels during much of the pre-dinosaur era were lower than today, which might have limited the metabolic resources available for maintaining large, energy-hungry brains. The absence of certain ecosystem types, particularly complex terrestrial environments, might have limited the evolutionary niches where intelligence would be most advantageous. The probability also depends on what we mean by civilization. If we're talking about a technological society comparable to modern humans, the requirements become much more specific. Such a civilization would need not just intelligence, but also the motivation and ability to manipulate their environment on a large scale. This might require particular combinations of environmental conditions, social structures, and evolutionary pressures that would be much rarer than intelligence alone. On the other hand, if we allow for forms of civilization very different from our own, the probability increases significantly. A biotechnological civilization that worked with living systems rather than manufactured tools might have been much more likely to evolve in ancient marine environments. A society based on chemical communication and environmental manipulation might have been possible much earlier in Earth's history. We also need to consider the probability of preservation. Even if multiple intelligent species evolved over hundreds of millions of years, the chances that we would find recognizable evidence of any of them depends on geological processes, largely beyond their control. The more ancient the civilization, the less likely it is that any trace would survive to the present day. When we factor in all these considerations, what probability should we assign? It's impossible to give a precise number, but we can say that the possibility is not negligible. The combination of vast timescales, evolutionary precedents for rapid cognitive evolution, and diverse environmental conditions makes it plausible that intelligence could have evolved in the pre-dinosaur era. Perhaps more importantly, the probability is high enough that the possibility deserves serious scientific investigation. We don't need to believe that ancient intelligence definitely existed to justify looking for evidence of it. We only need to believe that it's possible enough to warrant the effort of searching. In the end, the probability game tells us that while ancient intelligence is far from certain, it's not so implausible that we should dismiss the idea without investigation. The universe has surprised us many times before with phenomena we didn't expect and couldn't have imagined. Perhaps the biggest surprise of all is waiting to be discovered in the deep history of our own planet. If we found undeniable proof today that an intelligent civilization existed on Earth before the dinosaurs, the implications would extend far beyond paleontology and geology. Such a discovery would fundamentally alter our understanding of intelligence, evolution, and our place in the universe. First and most obviously, it would prove that intelligence is not unique to humans or even to our evolutionary lineage. We already know that other species display cognitive abilities, but discovering an ancient technological civilization would demonstrate that intelligence can evolve to human-like levels independently, under very different conditions, and in very different forms. This would suggest that consciousness might be a much more common outcome of evolution than we currently believe. The discovery would also revolutionize our understanding of evolution itself. The traditional view sees evolution as a gradual, progressive process, with intelligence as a recent and unlikely achievement. The evidence of ancient intelligence would suggest that evolution can produce complex cognitive abilities much more quickly and repeatedly than we thought. It would imply that given enough time, intelligence might be almost inevitable, rather than extraordinarily improbable. This has profound implications for astrobiology and the search for extraterrestrial intelligence. If intelligence has evolved multiple times on Earth, then it might be relatively common throughout the universe. The Fermi paradox, the question of why we haven't detected alien civilizations, might not be because intelligence is rare, but because civilizations tend to be separated by vast spans of time rather than space. The discovery would also force us to reconsider the relationship between intelligence and technology. If an ancient civilization developed along completely different technological lines than our own, using biological rather than mechanical tools, it would expand our conception of what technology can be. This might help us recognize forms of intelligence and technology we've never imagined, both in our search for extraterrestrial life and in our understanding of non-human intelligence on Earth. From a philosophical perspective, such a discovery would be simultaneously humbling and inspiring. Humbling because it would demonstrate that humans are not the first or only intelligent species our planet has produced. Our achievements, remarkable as they seem to us, would be revealed as part of a much longer tradition of consciousness and creativity that stretches back hundreds of millions of years. But it would also be inspiring, because it would show that intelligence and consciousness are fundamental features of our planet's history, not recent accidents. It would suggest that the universe itself tends to produce minds capable of understanding and appreciating their existence. Rather than being alone in an indifferent cosmos, we would be part of an ancient lineage of conscious beings stretching back to the dawn of complex life. The discovery would raise profound questions about the nature of consciousness and intelligence. How many different ways can a mind work? What forms might intelligence take under different evolutionary pressures? Are there aspects of consciousness and cognition that we've never experienced because our particular form of intelligence is just one solution among many to the challenge of understanding and manipulating the environment? It would also force us to confront uncomfortable questions about the fragility of civilization. If previous intelligent species had existed and then vanished so completely that we've found almost no trace of them, what does that suggest about the long-term prospects for our own civilization? Are we destined to follow the same pattern of rise and disappearance, or can we learn from their example to create something more enduring? The discovery might also reveal new approaches to some of our most challenging problems. If an ancient civilization had developed sustainable technologies that worked in harmony with natural systems rather than against them, understanding their methods might provide insights for addressing climate change, biodiversity loss, and other environmental challenges. Their solutions to the problems of consciousness and society might offer alternatives to the approaches we've developed. Perhaps most intriguingly, such a discovery would open up entirely new fields of scientific inquiry. Xenoarchaeology, the study of alien artifacts and civilizations, would become a discipline focused on our own planet. We would need to develop new methods for detecting and interpreting evidence of non-human intelligence, new frameworks for understanding alternative forms of technology and society, and new approaches to the question of what intelligence really is. The cultural and psychological impact would be enormous as well. Human societies have always defined themselves partly in opposition to the natural world, seeing intelligence and culture as uniquely human achievements that separate us from the rest of nature. Discovering that intelligence and civilization are actually ancient and natural phenomena would require a fundamental shift in how we see ourselves and our relationship to the planet. In the end, such a discovery would not diminish human achievement, but would place it in a much larger and more magnificent context. We would no longer be the only conscious voices on Earth, but part of a cosmic conversation that began long before we existed and will continue long after we're gone. Rather than being isolated accidents in an unconscious universe, we would be the latest speakers in a dialogue between mind and cosmos that stretches back to the very origins of complex life on Earth. Whether or not a civilization existed on Earth before the dinosaurs, exploring this possibility reveals something profound about the nature of time, knowledge, and existence itself. We live in a universe where the past is largely inaccessible, where most of what has happened leaves no permanent trace, and where our understanding of reality is built on the tiny fraction of events that somehow manage to survive the relentless erosion of time. This should make us humble about what we think we know. The history we've constructed from fossils and rocks represents an almost infinitesimally small sample of everything that has occurred on our planet. For every story we can tell about the past, there are millions we will never know, entire worlds of experience that have vanished so completely they might as well have never existed. The possibility of ancient intelligence forces us to confront the vastness of this unknown. If conscious beings lived, thought, loved, created, and died hundreds of millions of years before the first dinosaur, their entire existence has been compressed into a few chemical traces in ancient rocks. If that, all their achievements, their struggles, their discoveries and failures, their individual lives and complex societies, reduced to nothing more than mysteries we're only beginning to imagine. This perspective transforms how we think about our own moment in time. We are not the culmination of a long, inevitable progression toward consciousness and intelligence. We are just the latest experiment in awareness, the newest attempt by the universe to understand itself. Before us, there may have been others. After us, there will likely be others still. This doesn't diminish the importance of our own existence, or the value of what we're trying to achieve. If anything, it makes each moment more precious, each discovery more remarkable, each act of compassion and creativity more significant. We are part of an ancient tradition of consciousness that may stretch back to the very beginnings of complex life on Earth. The search for evidence of pre-dinosaur civilization is really a search for our deepest roots, an attempt to understand not just where we came from, but what consciousness itself represents in the cosmic story. Whether we find definitive evidence or not, the search itself expands our conception of what's possible and reminds us that reality is far stranger, deeper, and more wonderful than we usually allow ourselves to imagine. In the end, the question of ancient intelligence reflects our own deepest concerns about meaning, mortality, and our place in the universe. We want to know if we're alone, if consciousness matters, if the universe tends toward awareness and understanding, or if these are just brief accidents in an otherwise unconscious cosmos. The possibility that intelligence has emerged multiple times on Earth, that consciousness is a recurring feature of our planet's history, rather than a unique recent development, suggests that awareness and understanding are not accidental but fundamental aspects of how the universe evolves. Mind may not be separate from nature, but one of nature's most profound and persistent expressions. Perhaps the most important insight from considering pre-dinosaur civilization is not whether it existed, but what the possibility tells us about the relationship between consciousness and time. We tend to think of awareness as something that exists in the present moment, but consciousness also reaches backward and forward, connecting past and future in ways that transcend the immediate experience of any individual mind. If ancient civilizations existed, they contribute to this cosmic conversation even in their absence. Their struggles to understand their place in the universe echo our own. Their attempts to create meaning and beauty in a challenging world resonate with our deepest aspirations. Whether we ever find proof of their existence or not, they exist in our imagination as reminders of what's possible, what's precious, and what's ultimately at stake in the ongoing adventure of consciousness on Earth. The deep mystery of time ensures that most questions about the past will remain forever unanswered, but asking them changes us, expands our perspective, and connects us to the vast community of minds that may have wondered about these same questions across hundreds of millions of years. In that sense, we are never truly alone, but part of an ancient and continuing conversation between intelligence and the cosmos, a dialogue that began long before us and will continue long after we're gone. The question of what came before is also a question of what comes next, and what our own brief moment of consciousness might contribute to the eternal mystery of existence itself.